Hey everyone, so it's been asked if I would do a video to help with this business of using even functions or odd functions to help streamline integrals. So remember that an even function has what we call y-axis symmetry. So for example, this f of x equals x squared is a classic even function. It's symmetrical around the y-axis. So the right side is identical to the left side. Whereas an odd function has what we call origin symmetry. So that looks like a situation like this sine function, where around the origin, if you were to rotate this and just spin the page, right, that's still the basic sine function, just rotated upside down, and it's still identical to what it was when it was right side up. So that's what origin symmetry is like. If you imagine a pinwheel spinning it, and rotating it 180 degrees so that the positive y's point downwards, if you get an exact duplicate of the picture, then it has origin symmetry. Okay, so that said, the cool thing is, remember that integrals have to do with area between the curve and the x-axis. So if you have a situation like this, where we want to evaluate the integral from some number and its opposite sign, so that you're going basically the same distance on either side of the y-axis, so that your boundaries are the exact same distance on either side of the y-axis, then with an even function, as in this case, note that you'd be figuring out the area between the curve and the x-axis. And notice that because of the y-axis separating this even function into two identical halves, then this area to the left of the y-axis is going to be identical in size to the area to the right of the y-axis. So with an even function, if you're going left and right the same amount, and those are your boundaries in your integral, then it's a pretty clever thing that you can do, though you don't have to do this, but a clever thing you could do is recognize that, hey, I could just figure out the area from the halfway point, which is the origin, up to 2, and then just double that. And that's going to be the same thing as this value right here. I mean, of course, you can figure this out. You can see the difference in the advantage. If I just figure this out normally, that's x cubed over 3, and I could go from -2 to 2, which just means I'm plugging in the 2, subtracting the -2, and then, voila, that's going to be 8/3, and we're going to be subtracting -8/3. Because we're subtracting that negative, it's just doubling the 8/3 that we have here, so that's 16/3. So all I'm saying is that the alternative is you could go, okay, because of that symmetry, I could just go from 0 to 2, in other words, the halfway point to 2, and just double that. So here's the reason that that's a little bit advantageous. So, oops, sorry, that should be an x squared right there. Sorry, everybody. So this would be x cubed over 3, just as it was there, but instead, this time we're going from 0 to 2, and we're just going to double that answer. So the advantage is if I get to put in the 2, but putting in 0 is just going to delete that term, so no need to even write that down, and that's a little easier to calculate, perhaps, because that's just going to be 8/3 times 2. Yep, that's our 16/3 again. Yay. So maybe a little easier to calculate by thinking of it that way, and you get to take advantage of having a 0 that's really easy to work with. Now, look at this odd situation. So with an odd function, remember it's area between the curve and the x-axis. So with an odd function's origin symmetry, we'll have this portion of it, which is a negative area, and then we'll have this portion, which is an identical positive area. And so since these are going to be identical in size, if I do the integral from -2 to 2 of the sine of x dx, well, that's just going to have to equal 0. I don't even need to go through the process to get that. Of course, you could. Sorry, that's not -2. Oh my goodness. Sorry, I'm rushing. That should be negative pi over 2 to pi over 2, my boundaries here. So that's just going to be 0. No need to go through the process. Of course you can if you want to. You know, it's not going to hurt anything. It's just recognizing symmetry allows you to quicken this up. If you go through the process, the antiderivative of a sine is the opposite of the cosine. And then we'd have to evaluate going from negative pi over 2 to pi over 2. So that's going to be negative cosine of pi over 2 minus a negative cosine of negative pi over 2. Cosine of pi over 2 is 0, so that's just going to be negative 0 is 0. This will be adding. Cosine of negative pi over 2 is also 0. Yeah, that's 0. Okay, so you get to avoid going through all of that. So how is this useful? All right, so check this out. So if you have something a little more complex looking like this, if I were to graph that entire polynomial function, yeah, that might not look odd or even, but remember, one of the fancy things about integrals is that you're actually integrating every one of these terms separately. So a clever thing you could do is to separate this into individual separate integrals. And remember, a constant can come across the integral. So each one of these can be viewed as its own little separate integral from negative 2 to 2. And then what you can do is begin evaluating, well, how about each one of these individual things? So one of the things, fancy things you could do is to, if you're not sure whether that's an odd or an even function, well, one way you could do, or test it, is just graph it and see. So x to the 9th, if we graph, yep, that's an odd function. So since we're going from the same distance to the left and right of the origin where that symmetry is occurring, since it's origin symmetry, I know this entire integral answer is going to be 0. I don't even need to mess with it. Same thing with this one. That's gone. Okay, that's an even situation. We already know x squared is an even function. So I could streamline this one by just going, instead of negative 2 to 2, go from 0 to 2 of that x squared dx and just double it. Now it's already doubled there, so doubling the 2, it just makes that a 4. And then this one is also an even function, so a constant is going to be identical to the left and right of the origin. It's just a flat line. So what I could do for this one is, again, I could go from 0 to 2 and double that. There you go. So that more complicated integral can streamline to this, and then I can just evaluate this thing. So that's an x cubed over 3. We're just going to go from 0 to 2. This is going to be 2 times 10x, and we're going to go from 0 to 2. Well, that's just going to be a 20x. So if I plug in my 2, that's 2 cubed over 3. Don't need to plug in the 0 because that'll just disappear. Plug in the 2 here, that's a 20 times 2. Don't need to plug in the 0 because that would just be 0. All right, so here we go. So this is 4 times an 8/3 minus 40. So that is 32/3 minus 40. Get a common denominator, which would be 3. So that's 32/3 minus, 120/3. So that's going to be a negative 120, take away 32, so negative 88/3. Yay! So it just streamlines things, makes things a little faster perhaps, if you happen to notice the symmetry. If you don't, no big deal. You can just work the definite integral the regular way, and it'll come out just fine. It just speeds things along. That's all.